Good afternoon. Welcome to the ninth annual Forensic Science Symposium virtual poster session. The name of this presentation is Potassium Phosphorus Nitrate Detection and Spectral Segmentation using Polarized Hyperspectral Imagery in High Reflective Glare Environments. This was work done in collaboration with my summer intern, Jack McCarthy, from the University of Dayton, Department of Computer Science. My name is Nicholas Scott, and I'm from Riverside Research. I first would like to give an introduction. Military and law enforcement organizations are often tasked with target detection and scene characterization in environments where light and scatter intensity is high. Mitigation of photonic noise is necessary for high resolution target detection and machine learning based pattern recognition algorithms to produce reliable intelligence. Polarized filters are a possible method for ambient glare reduction by allowing only certain modes of the electromagnetic field to be imaged, providing greater scene contrast. In the summer of 2019, an experiment was carried out utilizing a polarization lens attached to a Resonant incorporated hyperspectral imagery camera for the purpose of exploring the degree to which polarized HSI scenes allow for improved or degraded target detection, image segmentation, and feature extraction. This work has implications for understanding image structure suffering from reflective glare, a potent issue inhibiting law enforcement and defensive agencies from engaging in optimal performance. Potassium phosphates and nitrates are ingredients for the creation of explosives, making this work of some importance to organizations whose work is related to explosive material analysis, criminal analysis, and crime prevention. The experimental setup is as follows. An 8-foot square white tarp was laid on a grass lawn and sand and cow manure was laid on top of the tarp. The sand and manure target was approximately 22 feet from the camera head, which was approximately 5 feet above the ground. This produced a 13-degree angle descent with the horizontal. Ambient lighting conditions were sunny skies and the average air temperature was 90 degrees. It was very hot that day. 3 HSI cues were taken of the target using the HSI camera with no polarization filter, a horizontal polarization filter, and a vertical polarization filter. Each HSIQ possessed 800 scan lines where a single line had 900 pixels, and the rest of the specs for the HSI camera are shown on the right. For those of you who've never seen HSI data, it's basically an image in X and Y, which is shown on the right, but then you have different spectral bands or wavelengths, which are capturing the information, the spatial information. So you basically have a stack of images with respect to wavelength. And this wavelength spans between 300 and 1050 nanometers. The HSI 300 band sample spectra of manure and sand is shown in this image. Sample HSI spectra for sand and manure for no polarization and horizontal polarization data sets are shown. The sand spectral signature, which is shown in green and red, has a higher spectral amplitude than the manure spectral signature, which is shown in blue and black due to its high reflectivity. Spectral amplitudes for the horizontally polarized data, shown in green and blue, are slightly greater than for the non-polarized data, shown in red and black. Principal component analysis was performed on the unpolarized light 100 by 100 pixel image chip, which is shown in this image. Principal component 1, 2, and 3 are shown from left to right. And what you can see is basically the first and the second PC images exhibit significant contrast. In the first PCA image in dark blue, you see the manure. Aqua green, you see the sand, and then in the upper left-hand corner, you see the tarp, which is shown in basically in red. Again, you can see strong contrast in principal component 1 and in 2, with a slight degradation in principal component 3. The same sort of principal component analysis was done for the horizontally polarized image chip. Again, we see that the first and the second PC images For the horizontally polarized imagery exhibit significant contrast. Again, in the first PCA image in dark blue, the menorah, aqua green is sand, the red area is the top. And again, as we saw in the previous one, but it's much stronger here, the PC3 or this third piece on principal component suffers from strong noise degradation. So again, left to right, PC1, PC2, PC3. In the first and second PCs, very strong contrast, and the third, significant noise degradation. Much more significant than you would see in an unpolarized case. Eigenvalue spectra for the non-polarization case, the vertical polarization case, and horizontal polarization case were calculated. The eigenvalue spectra are shown on the right-hand side, where the non-polarization case is shown in black, and the vertical and horizontal polarization cases are shown in red and blue, respectively. The eigenvalue spectra for all three cases demonstrate that large amounts of variance is captured in the first PC, or principal component. Vertically and horizontally polarized spectra have higher spectral amplitudes and attain spectral elbows slightly earlier than the non-polarized spectrum. What this all means is that the polarized imagery is efficiently pushing more energy into fewer spectral bands. This is actually good because what it's telling us is that if you compare the vertical in the horizontal polarization cases with the non-polarization cases, you will find that you're getting the same information, but it's just appearing in a fewer number of bands. And this actually bodes well for polarization HSI analysis, because what it's saying is that we can pull out information efficiently, basically using less power and less processing. Competitive leaky learning was the first machine learning algorithm that we used to try to get a handle on seeing contrast when looking at the data that comprises three polarization states. Competitive leaky learning clustering is a neural network based method for clustering spectral signatures. The way that it works is that for a data set, it takes pixels, which are also spectral signatures, and places similar pixels in the same group, such that menorah spectral signatures are with menorah spectral signatures, sand spectral signatures are with sand spectral signatures, and so on. A clear four cluster segmentation heat map for the non-polarized and polarized HSI can be obtained, and that's what you see in the top. For the first two cases, we have menorah in black, the menorah and sand mixture in dark orange, the sand in yellow, and the tarp in light orange. But for the horizontally polarized case, which is the third case, we have menorah in black, menorah and sand in light orange, sand in dark orange, and the tarp in yellow. Again, we can obtain a very clear segmentation of the data using this machine learning algorithm. So the results look pretty good. We don't see much difference in the polarization states, but in the next imagery, in the next examples, I'll be able to show you that in fact, though the segmentation is strong with the competitive leaky learning for all cases, there are subtle differences. We also perform a distance metric analysis of the data. In particular, we use the Kullback-Leibler divergence and a Bhattacharya distance, which are both sensitive to covariance, as ways to calculate the distance between the sand and menorah classes. Again, we're trying to parameterize the distance between the sand and menorah classes. Bigger distances actually are great for us here because that means stronger separation power in the data set. So we want to see strong contrast between the sand and the menorah, and which means a large value for the distance metrics, or the large values for the KLD and the BD. What we see in the data is that the KLD for the sand and menorah classes for the horizontally polarized HSI are slightly higher than for the non-polarized and vertical polarized HSI, irrespective of the number of spectral components or virtual dimension used. The BD, on the other hand, for Santa Menor classes for the horizontally and vertically polarized HSI are slightly higher than for the non-polarized HSI, irrespective of the number of spectral components or VDUs. So what this means is that the horizontally polarized imagery class separation power is slightly higher than for the non-polarized imagery case. So what we see in this analysis is that the horizontally polarized lens does give us a slight advantage. Our conclusions are that the HSI target detection power is slightly augmented via the use of a horizontal polarization filter. This result is consistent with known reflectance polarization photonics. What I mean by this is that it's well known that when light scatters or is reflected off of ground targets, it reflects back to us in a horizontally polarized mode, and our results corroborate this. We've developed a machine learning based methodology to rigorously evaluate non polarized and polarized imagery, but more experiments under different light conditions are needed to provide more comprehensive results. This last slide shows my full-fledged poster as I had it initially, and the points are on the left-hand side again. HSI target detection power is slightly augmented via the use of a horizontal polarization filter. We developed a field methodology to rigorously evaluate non-polarized and polarized imagery, but more experiments under different light conditions are needed to provide more comprehensive results. My email address is at the bottom of the poster, and I want to thank you for taking the time to listen to my presentation.